To start off with, we're going to look at inequations as opposed to equations, and it's pretty much the same thing. It's just that instead of an equal sign, we've got a less than or a greater than sign, and instead of a single solution, we end up with multiple solutions. That's usually the difference. Okay. But there are a couple of important things to keep in mind about that inequality sign. If you multiply or divide by a negative number, then the inequality sign will change around. Or as I just tend to remember it, if you change the sign, you change the sign. Okay? Change the sign of the number, you change the sign of the inequality. The other one to keep in mind is if you were going to turn both sides upside down, then the inequality sign will change as well. Okay, so that's the other situation. That's less common when we're solving equations, but keep that in mind. Obviously a very simple one, but just to illustrate some ideas. 6x is less than 36, just like an equation. Alright, I'll divide both sides by 6. X is less than 6. Now sometimes with these sort of questions we ask for graphical solutions, a picture, which just simply means let's plot them on the number line. Here's our number line. Don't get obsessed with the 0. Some people think, oh, I've got to put 0 on the number line. No, it's just a number. The number you're interested in, maybe one either side. There I am at 6, going to the left. The big difference with inequations and equations is we can have more than two sides. So we might have one like this, where it's in the middle of two numbers. Still the same idea though. Whatever I do to one thing, I just do to everything. Move the 6 into both sides, and we get minus 4. Less than or equal to minus 4x, less than or equal to 8. Divide everything by negative 4, but if you change the sign, you change the sign. But that's ugly. You look at that and go, oh, yuck. Oh, so much better. So much better. Now, x is in between minus 2 and 1, and if we plot that, that's what we get. And the reason I say that's much better is if you look at the graphical solution and you look at the algebraic solution, essentially they look the same. X is in between negative 2, which is on the right hand side, 1 is on the left hand side. It matches the picture nicely. Which brings me to this. The correct, in inverted commas, way of writing inequalities. And that's what I'm saying. The algebraic solution should look like the geometrical solution. It's a picture of the algebraic solution. So something like that. We say x is greater than 5. Look, the arrow's pointing in the same direction as the inequality sign. Everything's going that way. We don't write it as 5 is less than x. Because also think about what you're saying. The question is, what is x? So you answer it and saying x is greater than 5. You don't say 5 is less than x. The question was not about 5, the question was what about x? So you're answering what is x? This one here, something like that. Well then I write 4 is less than x is less than or equal to 6. Not 6 is greater than or equal to x is greater than 4. It doesn't look like the picture. And you certainly wouldn't write something like that. X is greater than 4 or x is less than or equal to 6. That's just plain wrong. So you could claim the second one there is actually still correct, but there's no way in the world you can claim that final one is correct, simply because of the use of the word or. Find a number that's greater than 4 or less than or equal to 6, well I claim you could pick any number you like. And it would satisfy that, because you're saying it's this or it's this. No. It would actually be and, not or. Ones that are on the outside of 2. Then that's how I write it. Again, it looks like the picture. X is less than or equal to 4, or x is greater than or equal to 6. And in this case, it is or, because it would be impossible for it to be and. Find me a number that's less than or equal to 4 and it's greater than or equal to 6. You can't do it. That's impossible. So, or is the correct word there. That just looks strange. Okay, technically it is the same answer, but it doesn't look like the picture. It's horrible. It looks horrible. And oh my goodness, I've seen this sort of thing before too. No, just plain wrong. That one is wrong. There were linear equations, our examples before, but of course we can have all sorts of equations, which means we can have all sorts of inequations as well. So quadratic inequations, something like this. Well, if it was an equation, I'd say what multiplies together to give the last number, adds to give the middle. I still do the same thing. But now this is where it's different. See, in an equation I would say, well, either x plus 6 is equal to 0 or x minus 1 is equal to 0. But I can't use that same idea here. I can't say either x plus 6 is less than 0 or x minus 1 is less than 0, because what happens if they're both less than 0? You wouldn't get a negative number, you'd get a positive number. Again, the picture helps. If I was to draw this, I've got a parabola. I know the x-intercepts are minus 6 and 1. It's concave up. And now I think about what it's actually saying, and what it's saying is, well, what values of x is the parabola below the x-axis? When is it negative? When are the y values negative? And I can look at the picture and I can say, well, it's all along this section here. But hey, I'm only interested in the x values. So if I was to plot all the x values for all those points, I'd end up with the section in there. Therefore, my answer is x is in between minus 6 and 1. If I had this one, minus x squared minus 3x plus 4, personally, I just prefer it to be a positive x squared. That's just me. So I'm going to multiply everything by negative 1, but if I change the sign, I change the sign. That factorizes. And this time I'm saying, hey, when is this parabola above the x-axis? Again, I'm sure it's that piece of the parabola. I'm only interested in the x values. And so there's my solution. Now, whether you physically draw the parabola or not, I guess it doesn't really matter. But the key points are still the solutions to the equation. They become the x-intercepts. Whether or not they're included or not is another matter. And you could just simply pick a number and test and see where you are. That's known as the critical points method, and it's used for a lot of inequalities. But with quadratic inequalities, what we do know is the solution is going to be one of those two situations. Because it is the parabola we're talking about, and we're always saying when is it above or when is it below, I will always get something that's either in between those 2 points or on the outside of those 2 points. Has to be one of those two. But as I say, if you want to solve an inequation, by far I think the most efficient way of doing it is forget that it's an inequation, just solve the equation, get you what we call the critical points, those key points of the solution, and then just test the different sections to see, am I there or am I not there? Absolute value inequations then. And this is where the definition becomes really, really important. So we say either x plus 5 is less than 2 or the negative of x plus 5 is less than 2. Because what we're really saying is, if we were to draw that picture, we would be drawing the two branches of the absolute value curve. One of the branches would be x plus 5, y equals x plus 5. The other branch would be y equals the negative of x plus 5. We're saying when is this below 2? So both branches have to be below. Solving one of them, I get less than negative 3. Solving the other one, I get x is greater than negative 7. I can draw myself a picture here and say, well, hang on, okay, it's less than negative 3, but it's also greater than negative 7, so where am I? Well, clearly it's where I've both got blue and green. I'm in the middle for this one. For here, 3x plus 2, either 3x plus 2 is greater than 1, or the negative is, well, the left one gives me x is greater than or equal to negative a third, the right hand side gives me less than negative 1, I'm here, and I'm there. Well, in this case, we're not talking about the intersection because there is no intersection, and clearly there are solutions. So we must be on the outside. We got both of those. It's an or situation. But again, you could simply solve it like an equation, find those two solutions, just test to see where you are. And another way you could do it is actually turn it into a quadratic. So here's that same question. Square both sides. Now I can do that. Squares are always positive, same as absolute values, so it's going to work nicely. I get x plus 5 squared is less than 4. Solve that inequation. Okay, there's the mass behind it. We get x is in between negative 7, negative 3. The same solution. The second one we looked at, again, let's square both sides. Solve it, we get the same answer. Personally, I don't do it that way, but it is a way you could do it. it would work. But remember, whenever you transform an equation into something else, just make sure that your solution is a solution to the original equation, not just the one you've transformed it to. Pronumerals in the denominator create another situation. Let's start with a very simple one. 1 over x is greater than or equal to 3. When is our hyperbola, if you like, above y equals 3? I'm going to do it using critical points. As I say, it's by far the most efficient way of solving inequations. What are the key points in something like this? Well, we know we've got a problem with the domain. The bottom of the fraction can't equal 0. That's going to create a critical point because that's an exclusion in the domain. It can't be a solution. So I know x can't equal 0. I've got one critical point. I will go and solve it as if it's an equation, not an inequation. And if I do that, I get x is 1/3. There are my critical points. I can put those on a number line, remembering that 1/3 is included, but 0 is not, because it was a critical point because of the denominator situation. Pick a point. Oh, okay, -1. I'm not saying you'd actually write this down, but -1. Oh, substitute it in. Is -1 greater than 3? No, it's not. So I know I'm not there. Well, what about a quarter? The reciprocal of a quarter is 4. Is 4 greater than 3? Yes it is. So it must be included. That section is there. And just to make sure, let's pick a number bigger than 1/3. Oh, 1. Substitute 1 in. Is 1 bigger than 3? No, it's not. There's my solution. So that's my answer to the inequation. 2 on x plus 3 is less than 5. Bottom of the fraction is causing me a problem. I know x can't equal -3. Solve it like an equation, and I get 5x is -13, x is -13 on 5. There's my two critical points. In this case, both of them are not included because it's just a less than, not a less than or equal to. Pick a point to test. I'm always going to go with 0. It's just so much easier. 2/3 less than 5. Yep. And so, bingo, there's my answer. Thank you very much. It's very quick for ones like that. 1 on x is greater than or equal to 3. So what they do is multiply by the denominator squared. Why the denominator squared? Because if you just multiply by the denominator, it's not going to work. Because you don't know, is that denominator positive or negative? Because if it's negative, the sign's going to change. You have to multiply by a positive number to ensure that that sign does not change. So you multiply by the denominator squared. You get multiply both sides by x squared. You end up with a quadratic inequation. So like the absolute value one, we're turning it into a quadratic. And we know how to solve quadratic inequations. So we go and solve that one, and we end up with our answer. As I say, the most popular method, but not the most successful method. Always take care of the domain, however. You see, that is not actually the answer, and that's probably one of the biggest mistakes that people using this method do. They've solved the new equation, they haven't gone back to see if it's a solution to the original equation, and of course x cannot equal 0. X can't equal 0, in other words, there's our solution. Okay, our other one, we'll multiply by x plus 3 squared. By the way, when you do this, for goodness sake, do not expand out. You are going to create a common factor straight away by the nature of what you're multiplying by. So there we go. It's already factorised for us thanks to that, and we get the solution. But remember, got to solve the original question, not my new question, and there we go. Okay. 5A.